Okay, it's a pleasure to introduce Enrico Barausse from SISSA, who today will talk about light bosons, compact objects, and gravitational wave.
Well, thank you. Thank you for the invitation. And today I'll talk about light bosons, compact objects, and gravitational waves, which is sort of a generic title, because I'm mainly, I'm a phenomenologist, or if you want, a gravitational physicist. So I didn't really know what to expect from this conference. So I decided to put a lot of things together. And in fact, let me give you, this doesn't work. Sorry. So I decided to put many things together, and hopefully you'll find at least some of them interesting. So first, I'll try to motivate why I'm interested in light bosons in the first place. Zoom is muted. No, please. My computer is muted. Speakers are off. It's off. Wait a second. Mute. One, two, three, test. Can you hear me online? No answer. Is there anybody online?
Yes, we can hear.
What is going on here? Sorry. Yeah, here. Okay. Oh, hopefully now things are under control. So why light bosons in the first place? So I'll try to motivate that, and then I'll try to delve into the phenomenology of light bosons and compact objects. So I'll talk about superradiance, which I don't think we touched upon in this meeting. And I will also say something about solitons and boson stars. So this will be the first half of the talk. So this will only rely, so superradiance relies only on having a scalar field with a light mass. Boson stars rely on having a scalar field with a non-trivial potential. And then in the second part of the talk, I will give more, I will add more ingredients and talk about scalar gravity in the context of modified gravitational theories. So I had prepared a few slides on scalarization, which Tanya already covered, so I think I'll skip that. And instead I will focus on other phenomenology that you can get when you consider non-minimal interactions for scalar fields. In particular, I will talk about screening of local scales and the effect on gravitational wave generation. So why light bosons in the first place? Well, scalar fields are ubiquitous certainly in cosmology. Think about inflation, think about dark energy and dark matter, also fuzzy dark matter. But they're also ubiquitous in string theory, from what I understand, although this is, and correct me if I'm wrong. So think about the Axiverse scenarios, think about the dilaton, or in general, think about the QCD axion. So in general, in particle physics, we have abundance of scalar degrees of freedom. But to me, the main motivation for which I'm interested in those is that they're useful as time models for phenomena for which we don't have a very good description. Think about, again, deviations from GR, and also dark energy. So we'll talk about the effective field theory of dark energy in the second part of the talk. So we'll be focused on light boson fields, or scalar fields, to be more precise. And by light, I mean anything less than 10 to the minus 10 eV. So this is considerably lighter than even the QCD axion. And this is the price to pay if you want to have effects for astrophysical black holes or in general in cosmology. So I said that I will be focusing on scalar fields, but most of what I will be saying is also qualitatively at least applicable to other hadicities, also to vector fields or to massive gravity if you believe there are massive tensor fields. So, so why are you interested in light bosons in the context of compact objects? Well, because when you have scalar fields with a potential, they can form self-gravitating configurations. So for that, you need scalar fields which are massive, because you want these scalar fields or these boson fields to avoid dispersion to infinity. And you want either time dependence or complex scalar fields or both. So as I will be trying to explain in the following. So if you have a time dependence and massive fields, you can construct what we call oscillatons, which are, if you want, models for alternative models for compact objects. If you have complex, massive, and time-dependent scalar fields, you can construct boson stars. So these are examples of self-gravitating configurations that you can build with boson fields. Also, if you, this is if you want only to have solitonic configurations. If you allow also for the existence of black holes, and if you try to entertain the possibility that there are light bosonic fields around black holes, you can also have very interesting phenomenology, such as the formation of clouds around black holes, formation of hairs, which Tanya covered already. So we'll be trying to say something about it. So in the first part of the talk, I will try to focus on the interaction between light scalar fields and black holes and the formation of what we call black hole boson condensates. So this slide, in fact, has nothing to do with black hole boson condensates, but it rather has to do with the Penrose process, which is one key ingredient to understand the formation of these black hole boson condensates qualitatively. So you all know the Penrose process. You throw a rock or a projectile at a rotating black hole. This projectile splits into two pieces inside the ergosphere. Inside the ergosphere, you can have trajectories with negative energies as observed by at infinity. So the piece with negative energy falls into the black hole, and therefore the second fragment escapes with a larger energy than the incoming bullet. And as a result, and of course, this efficiency, which is larger than 100%, comes at the expense of the rotational energy of the black hole. This is the classic Penrose process. You can also have a wave generalization of this Penrose process, which is called super-radiant scattering. So you can have an incoming wave which impinges onto the ergosphere of the black hole, and the wave is scattered with amplitude larger than it had in the first place. So this is known as super-radiant scattering, and it can lead to amplification, but only for frequencies, for wave frequencies, which are less than the rotational frequency of the black hole horizon, or multiples of it. So this is the super-radiant scattering or amplification condition. Omega must be less than m times the angular velocity of the horizon. So as you can see, where m is the azimuthal quantum number of the wave. So if you want, the angular momentum of the wave. So as you can see, the minimum m that you can have that can give rise to super-radiant amplification is m equals 1, which is a dipole. So this will be important in the following. So this super-radiant scattering of Penrose process is simply a way to extract energy from a black hole. But you can also make this process even more extreme by triggering an instability, and this is known as super-radiant or black hole bomb instability. So the idea is the following. I think I have it in the next slide. You place a mirror outside your black hole. This is, of course, a Gedanken experiment. So this is the effective potential for the perturbations. So when gravitational perturbations are reflected back from this mirror, they go back into the ergo region here, where they can again give rise to super-radiant amplification. So some energy falls into some negative energy falls into the black hole, and some positive energy is emitted. And then this process, because you have this mirror at infinity, repeats time and time again, and this gives rise to amplification of the perturbations inside the ergo region. This is known as black hole bomb instability or superradiant instability. It was dubbed black hole bomb. I think the story is interesting. I don't know if it is apocryphal or true, but it was discovered in the 60s and 70s, and the government was very interested in developing, of course, bombs. So they thought of this as a way to extract money from the government. So that's why they gave it this name. Essentially, yeah, so this is, as I was saying, a toy problem, but as Vitor showed 2 days ago, this can be actually realized in practice if you have a bump in your effective potential at infinity. In fact, this is an exercise that we did back in 2014 with Vitor and Paolo. So what we did was to put a ring of matter very far away from a black hole, and we looked at what happens to the gravitational signal. So we perturb the black hole, so we get this cascade of ring down modes. Then we have a secondary pulse due to the reflection from the matter at infinity. And if you repeat this process, if you wait long enough, this will give rise to a black hole bomb instability if the black hole is spinning, because you have reflection of these waves between the black hole and the ring of matter far away from the black hole, and this repeats the superradiant scattering time and times again. So similarly, if something dramatic or unexpected or happens at the surface, quote unquote, of the black hole, or at the would-be horizon of the black hole, you could have partial reflections of waves from the would-be event horizon, and this can also give rise to an instability if the black hole is spinning. So suppose you put a mirror at the very near to the horizon of your black hole, then you can have essentially a resonant cavity between this mirror and the peak of the effective potential. And this is also where the ergo region lies. So you can have waves traveling back and forth between the mirror and the peak of the potential, and at the same time, extract energy from the ergo region. And this is why we expect that spinning black holes with reflectivity, non-zero reflectivity, will be unstable to superradiant instability. So this is always the same idea of the echoes, but from a slightly different perspective, because the different perspective being given by this superradiant amplification. So this is all quite, if you want, exotic, and thus far it's not clear, I think, to you why I'm telling you all this in the context of light scalar fields. Well, the reason is that when you have a spinning black hole with a massive bosonic field, be it a scalar field, vector field, or a tensor field, you have a physical realization of this black hole bomb instability, because the mass of the scalar field prevents the scalar field from dispersing at infinity, and it plays the same role as the mirror. So this is something which was understood back in the 70s by Damour, Deruel, and Ruffini in 1976. So if you have a spinning black hole plus a light boson field, this gives rise to a superradiant instability. So importantly, it needs to be a boson field. This doesn't happen for fermions, essentially because of Pauli's exclusion principle. So you can't really accumulate or fit as many fermions inside the ergosphere as you would, as you are able with bosons, which do not have the exclusion principle. So to make a long story short, if you have the right mass, black holes with spins surrounded by a light boson field can become unstable. And the endpoint of the instability is a black hole with lower spin, because the superradiance actually extracts rotational energy from the black hole, and the black hole loses spin. So in this, this is from a paper with Paolo and Vitor, I forgot to put the reference. So in this work, we try to collect either existing or future measurements of black hole spins, which are here the dots with the error bars. And the shaded areas are the instability regions for different scalar fields of different masses. So you see from 10 to the minus 11, I don't know if you can read, to 10 to the minus 19 eV. These are crazily small masses, But you need such low masses because for the instability to be effective, you need the Compton wavelength of these fields to be comparable to the size of the black hole. So for instance, if you have a scalar field of 10 to the minus 13 eV, the Compton wavelength is of the order of tens of kilometers, so you're in the LIGO band. And if you measure black hole spins with LIGO and Virgo, you'll be able to probe this instability region. So the shaded areas where black holes should not exist. So for instance, here we have a bunch of measurements of black hole spins from, this is, well, this is for Lisa, yeah, these ones. These ones are existing measurements, electromagnetic measurements of black hole spins in AGNs. And as you can see, if you take them seriously, which perhaps you should not because they have systematics and so on and so forth, you could exclude the presence of very light boson fields. Yeah. So sorry, I didn't understand.
What physics when you have, this all these light fields, all these experimental constraints from particle accelerators against also, I guess.
Well, these are for these small masses. I don't think there are constraints. This is fuzzy dark matter. So as far as I'm aware, there are no constraints on this. The Lyman alpha. What I know for 10 to the minus 19 eV is Lyman alpha formation of structures. I don't know. I don't think there are constraints from accelerators on boson fields of 10 to the minus 19. Yeah. I mean, this is what is called fuzzy dark matter. So 10 to the minus 19 is probably my disagreement with Lyman alpha because it causes, it essentially prevents formation of structures on galactic scales. But those constraints come from with a sort of with a fine print attached. These spins, so these spins are measured with iron K alpha lines. So it's fluorescent emission lines from iron in an accretion edge and accretion disk, and the shape of the line is modified by the strong field, by the rotation, the frame dragging of the black hole, essentially. These others are with gravitational waves. This is with LISA. So these are fictitious measurements, future measurements. But these are measured electromagnetically with this iron K alpha.
So maybe one of those fields, just one of the bands, the green one.
Yeah.
Just rule out the black holes.
This rules out. Yeah, I'll show later that LIGO data already rule out 10 to the minus 13 eV. If you give me a couple of minutes. Yeah. So this is what you could do if you could measure the spin. It's slightly more complicated because we can't really measure the spins of the black holes in LIGO with very good precision. There is another way, again, based on superradiance, by which you can exclude. So this is if you can measure the spins, and measuring the spins is not really easy in general, neither with LIGO, neither with EM, electromagnetics. So I want to take a different, I forgot to start the time. I want to take a different route here. So I mentioned that the endpoint of the instability is a black hole with lower spin, but what happens to the scalar field? Well, the scalar field forms what we call a wig or a scalar condensate around the black hole. So the idea, which I will be presenting qualitatively, but which is rooted on actual calculations, at least in the decoupling limit, is that the scalar field develops a dipole configuration. Why dipole? Because the superradiant amplification condition, the first superradiant mode is the one with m equals 1, which is the dipole. So the scalar field extracts energy from the black hole and starts rotating in a dipole-like configuration. This is a nice figure from, I think, a paper by Vitor. And the black hole, as a result, loses spin. So what happens when the scalar field rotates? So if you have a rotating dipole in general relativity, because of the, and the frequency with which this dipole rotates is essentially proportional to the mass of the scalar field. So whenever you have a scalar field dipole rotating, simply by the quadruple formula, you will emit gravitational waves. So you will produce long-lived scalar dipole condensates co-rotating with a black hole, and this will produce monochromatic gravitational waves. So this, by the way, I should mention that this is an instability. So it doesn't rely on fine-tuned initial condition. It happens all the time when you have a scalar field with the right mass. So the endpoint of the instability is a black hole with lower spin and a rotating dipole configuration, which produces gravitational waves whose frequency is proportional to the mass of the boson field itself. So this for each and every rotating black hole, isolated rotating black hole in the universe, irrespective of the initial conditions. This is where this is where it saturates, where the instability becomes ineffective. So so this comes from the calculation. Yeah, okay, so the black hole with the instability will happen very fast. So the black hole will spin down very fast, and then you'll end up with this rotating configuration, which is much more lived than the instability. So first you have the instability, which is fast. Let me see it here, of the order of years. And then you have this rotating configuration. I don't know if it's correlated. The spin of the condensate is parallel to the spin of the black hole. Right. So sorry, what prevents this from firing off? Gravity. I know, because these are modes with negative energy. So these are modes with negative energy, which are inside the ergo region. So you can't disperse them to infinity. So when you have the Penrose process, so why can you extract energy? Because you create more and more modes with negative energy inside the ergo region, and they're trapped. They cannot go to infinity because they have negative energy.
No, we got it, because they're bound, they're created bound to the model, and they just don't have enough negative energy.
Yeah, but it's yeah.
They're massive states.
Yeah, these are quasi-bound states, in fact. Okay, so the point I want to make, I completely lost track of time, but hopefully you'll give me a 20-minute mark. So this happens these long-lived rotating scalar dipole clouds are predicted to exist around each rotating black hole in the universe. Now we are very used to the black holes observed by LIGO. Those are in binaries. There are many more isolated black holes in the universe than there are binaries. This is quite intuitive. So there are many more of these monochromatic gravitational wave emitters than there are binary emitters, such as those observed by LIGO. So somehow we should have seen this. So we can make this argument more quantitative and try to take astrophysical models for the population of all isolated stellar origin and supermassive black holes that exist in the universe, and try to compute what we call the stochastic background from this superradiant instability. So what I'm doing here, this is again from a paper with Vitor and Paolo of a few years ago. We take astrophysical models for the black hole population, and we assume that there is a boson field, or a scalar field to be precise, with a given mass, and we sum incoherently all the signals, gravitational wave signals, from these isolated black holes. Why? Because most of these black holes are far away. The signals have little signal-to-noise ratio, so you would expect to observe them as what we call a stochastic background, so an incoherent superposition of signal instead of a resolved source. So predictions from the various astrophysical models are here. They're given by different line styles corresponding to different versions of the models, because as usual in astrophysics, we have a modeling uncertainty. But the black curves are the sensitivity curves of LIGO Virgo at various observational runs, and LISA, which is a future gravitational wave detector. And as you can see, a boson field of 10 to the minus 12, 10 to the minus 13 EV should have already been detected through this stochastic background if it existed. So this is robust versus modeling of the astrophysics. So this is, I think, evidence that this scalar field of 10 to the minus 12 EV does not exist, or there is a caveat here, it doesn't emit gravitationally, which can happen if the scalar field is strongly coupled to electromagnetic waves, because one key assumption that I'm making is that this scalar field is only coupled minimally to gravity. So this is a possible loophole in the argument. And with LISA, you'll be able to probe even lower masses, which are even better for cosmology. As I mentioned, these models are also known as fuzzy dark matter models. So in fact, I'll not enter into the details. You can do this calculation literally on a piece of paper in 2 minutes if you know a little bit of the astrophysics. So we have a back of the envelope estimate of the level of the stochastic background. So irrespective, because sometimes when I give this talk, people tell me, okay, astrophysics, there are lots of assumptions and so on and so forth. Literally, these results come by multiplying 2 numbers. So we know from AGM measurements what is, for instance, the density of supermassive black holes. We know what is the efficiency of this scalar boson, scalar condensate gravitational wave emission. We multiply 2 numbers together and we really get the amplitude of the gravitational wave stochastic background. Yep. So this density of, this is the local, this is the density of black holes, supermassive black holes at redshift equals 0. Yeah. How much energy? Yeah, so I guess we could convert this 10 to the minus 9. So I would say it's 10 to the minus 12. This is for the gravitational waves emitted. Black holes, it should be, well, it should be larger than that. I think it's 10 to the minus 6, but I'm not, from what I remember. Also, yeah, I expect we extract 10 to the minus 3 of the mass of the black hole. Yeah, I have it in one paper. Yeah. And same for the LIGO band. Okay, so well, I'll skip maybe these 2 slides. So more interesting, perhaps, for this crowd, in a subsequent paper, again with the usual suspects here, we tried to look at a related question. So I mentioned that you can have this super radiant instability also in the presence of a mirror. So I mentioned that sometimes we think of exotic near horizon physics as parameterized by a reflectivity coefficient. So what we did in this paper was to assume that all isolated spinning black holes in the universe had a mirror near the event horizon. So perfect reflectivity. And we asked, what is the effect that this would have on the gravitational wave stochastic background? Say again? Perfect reflectivity in all frequency ranges. Yes, yeah, perfect reflectivity. And this gives right, yeah. No, you would expect a strong superradiance. No. No, but you put the, yeah, a mirror here. Yeah, there's an ergosphere, it's spinning. These are spinning black holes. Well, you can compute, yeah. Yeah. Yeah, you need to do a Laplace transform, of course, if you assume that your frequencies are.
If you look at the wave equation and you go down the division equation, you're going to find that the amplitude of the wave magnitude is the slightly wave is the same as in terms of it's a shifted wave. Yeah, but the other is the free analysis is the interactive state because it's a different state. So if you do it in time, if
But Peter, I think even if you do it in the frequency domain, you can get, because this is what we do in that paper, right? Because we do have the frequencies, and you see really the factor omega minus m capital omega in the frequency domain. Yeah, not the scattering. Yeah, I guess in the scattering experiment, yeah. But certainly, but if you do a boundary value problem in the frequency domain, you should find this instability. But I can show you the reference later. In fact, it's a paper by Paolo that computes this, by Paolo and Elisa. So hopefully you're right. No, but it also makes sense physically. You agree with yourself? Good. That's okay. So since black holes with the mirrors, quote unquote, have superradiant instability, you can again compute the stochastic background from a population of astrophysical, a well-motivated astrophysical population of spinning black holes. And you find again a stochastic background of gravitational waves produced because you form again, because of the same argument as with the light boson case. So here, in fact, it's not really, you don't really form a condensate. You don't have a scalar field, but these are the gravitational waves that form from the instabilities, essentially the tensor modes. So, and again, so what we did here was to put a mirror essentially at a Planck length from the event horizon of the black hole, and this is excluded to many orders of magnitude by even LIGO 01. These are the bounds on the stochastic background from LIGO 01. It will be the same case with LISA when we have LISA. So then we try to parameterize this effect a little bit more instead of putting, so we try to parameterize the time, the light crossing time of this. So the idea here is that we have something which is not a black hole. And so we try to parameterize the distance between two subsequent echoes. So T naught is the time it takes for the signal to be reflected by the mirror. So the idea is that the signal gets lost somewhere inside this would-be black hole, and then it gets emitted perhaps 10 to the 10 light crossing times later, or 10 to the 12, or 10 to the 14 light crossing times later. And this quenches the instability, but still you're in wild disagreement with current data. So I think what this tells us is that, perhaps expectedly, that perfect reflectivity of the event horizon is no-go. I don't think it can be made. It can be made in agreement with data. So you need partial reflectivity, or you need some sort of viscosity damping this instability. Okay, so how am I doing with time? 30 minutes left. Okay, so very quickly, so I have a lot of things in this talk. Usually I give 3 talks out of this. So today I'm trying to merge them. So so other interesting things that you can do with the light bosons are, as I was saying, solitonic configurations. These are known as boson stars in my field. In the particle physics field, for some reason, they're known as Q balls, perhaps in the flat space-time limit. So in some regime, they're called Q balls. Sometimes they're called solitons. And this is quite interesting because you can get them with really a minimal modification of the ingredients that I gave you thus far. So far, I only had a scalar field with a mass. So here I have 2 fields. So phi is a complex field with a U1 symmetric potential. And this potential has a self-interaction. So this is, yeah, so it's not just a mass, it has 2 parameters, the mass of the boson field, which is again very light, if you want to have a phenomenology on astrophysical scales, and you have sigma naught, which is a self-interaction potential. So also I want the scalar field to be time dependent, so I want it to be, to have this Fourier form. So this time dependence doesn't prevent me from having a time independent metric, because the time dependence essentially doesn't propagate in the stress energy tensor, because the potential only depends on the absolute value of the scalar field, because it's a U1 symmetric potential. So interestingly, this relatively simple Lagrangian gives rise to objects which can be very compact. In fact, they saturate the Buchtal limit. So we heard from Rami about the Buchtal limit, which is, I think, 4/9. So here we saturate not the Buchtal limit to court, but we saturate the causal Buchtal limit. So if you take the Buchtal limit and you impose that the speed of sound be at most 1, you get 0.35 or something. And with this Lagrangian, you saturate that limit. So this is quite a respectable compactness for something that is not at all a black hole and something which is by and large in agreement with data. Another interesting thing about these solitonic configurations is that they have quantized angular momentum, so you cannot spin with
Can you do it also with the
potential? You can do it with all sorts of potential. The reason why we chose this potential is that it saturates the Buchtal limit. So this particular potential allows you to so. But you're asking what happens if I add another term. Yeah, I see. I guess you can do it, but I don't know what the compactness would be. Maybe Paolo. Less compact for sure, but I don't know how compact. The sign is correct one. I don't know if this one is the correct one. Depends on your convention, but in the we use the correct. Depends on the signature. No, there's nothing exotic here. 10 minutes. Okay. So let me. Normally we define it as 95% of the mass, but the 95% of the mass of the scalar field. But the scalar field here is goes down quite. I mean, it's a Yukawa suppression at infinity. I think here in the paper we define it as 95%, the radius that contains 95% of the mass of the scalar field. No, but the reason why we believe it saturates the bound is that you can actually compute an effective equation of state for this scalar field. And in fact, we plot the speed of sound and it gets very close to 1. But yeah, you're right, it's a sort of a fuzzy statement. That's a good point. Yeah, that's why I'm not a big fan of boson stars, or because if you want to replace supermassive black holes, you need mass of 10 to the minus 19 eV. If you want to replace stellar origin black holes, you need masses of 10 to the minus 12, 13. No, you can, here. I mean, here you can get. No, the question, you can get all the masses you want. The question is whether you can get the right compactness for all of them. Yeah, so. Yeah, the compactness, okay, I don't have the mass. So there will be a mass radius relation, like for, it's the same as for neutron stars. So you can get different masses within reason. You can go to supermassive black holes if you have a scalar field which is in the LIGO range, but then not all black holes will have the compactness of 0.35. I don't, well, some of them, yes, for the low compactness, yes, but 0.22 won't be at the light ring, I think. All of them, yeah. Yeah, M over R. Yeah, so this will be 4. Yeah, 3. Yeah, here. Yeah, you're right. Yeah, 3. Yeah, 3 will be exactly at the light ring. Yeah, so maybe you'll run into problems with the QNMs. That is possible. So what happens? So one interesting thing that you can do before I devote 5 minutes to what I really wanted to say about effective dark energy. So you can also do simulations. So this is not something that you can do for many theories. You can do simulations, binaries. So, so there will be deviations from black hole waveforms in the spiral due to the tidal lobe number and tidal effects. And also these systems will lead to an earlier plunge, exactly because of what Rami was saying. So these, even though they saturate the Buchtal limit, they're still quite fat systems. So they touch quite early and they form long-lived post-merger phases. In fact, they also give rise to other interesting phenomenology. So, for instance, you see here the emission of this blob. This is a blob of scalar field which gets emitted post-merger with a speed of 10 to the 4 kilometers per second. So this imparts a kick on the post-merger remnant, which you could in principle test with data in the future. So in fact, what do the waveforms look like? So we tried to compute these waveforms in a semi-analytic, a bit dirty way, but this is the best we could do. So you see here, this is a system which has deviations in the spiral due to tidal effects, but also more prominently, it has deviations from black hole waveforms, which are plotted here in black, in the post-merger phase. So you see this almost monochromatic signal in the post-merger, which is due to the formation of a post-merger boson condensate, if you want, boson object. Yeah, there is no horizon here. Yeah, so these are the quasi-normal modes. Here you don't have the quasi-normal modes. Yeah, this is simply a rotating cloud, so it's simply a rotator, just like the condensate we had before. So this is the case of two boson stars, which give rise to a supermassive, if you want, boson star. Similarly, in other cases, you can produce a black hole. So here there are two boson stars that merge into a black hole. So the post-merger signal is exactly the one you would expect, but the in-spiral signal is different. So this is difficult to, unfortunately, to detect with, it's difficult to tell apart, to be more precise, black holes and boson stars with current detectors, but waveforms such as this will be definitely distinguishable with next generation detectors. Yep. But there is no quasi-normal, there is one mode that they observe here. This. The what? Yeah, no, but it could be, I mean, this depends on the mass of these are the same theory. So you could have both. So depending on the masses, you could have both. So there are also here, I didn't, so one reason why it's difficult to test this with current detectors is that if you have high masses, you see here the mass of the system can be as large as 100. This post-merger signal could be out of band. So I don't think this is in disagreement, to make a long story short, I don't think this is in disagreement with current data, although we didn't run a detailed analysis. Yeah, it's very difficult to, I think what is fair to say is that the one event among the 100 for which they detected the ring down, which is 150914, must have a post-merger signal, which is like this. So it could be either two boson stars or two black holes, but the remnant must be a black hole. But this doesn't mean that there is one other, we can talk about it. Okay, so last 5 minutes. Let me think how I can do this in 5 minutes. Okay, so I wanted to talk about also, so far we've only done minimally coupled scalar fields, one or two, real or complex, with a potential. So now I want to enlarge my imagination to encompass the whole Hordensky class, or how we also call it, or generalize it, the degenerate higher order scalar tensor theory class. This is a huge class of scalar tensor theories. So these are the most generic scalar tensor theories which do not have ghosts, Ostrogradsky ghosts. So it's a huge Lagrange, and this is only the Hordensky class. There are a number of free functions. DOST is even larger. So I want to focus in particular to this non-standard kinetic term. This is what we call K-essence. The reason being is that this is the, in this huge Hordensky class, this is with some caveats, the only term which is compatible with constraints from the propagation of gravitational waves. All the other terms are constrained if you require the scalar field to be the dark energy. This is an important caveat. If you don't require the scalar field to be the dark energy, you have all other terms, including the terms that Tanya was talking about. So in here, there is also the Gauss-Bonnet term. The Gauss-Bonnet term corresponds to G5 proportion to log of x. So it's a particular case. The case that Tanya was considering is one particular case. So let me show you, perhaps, I promise I'll show you just 3 slides. So why am I interested in this term? Because it gives interesting phenomenology at the level of, again, compact objects. So here I'm simplifying this Lagrangian. I'm considering GR plus this nonlinear kinetic term, K of x. X is the kinetic energy of the scalar field. And here, not only do I have the usual term, 1/2 x, I also have quadratic, cubic, and perhaps higher order terms. This is in principle a full series. I also have a conformal coupling to matter in the spirit, if you want, of Brans-Dicke theory. So there are 3 parameters here, which are beta, gamma, and alpha. This scale, lambda, is the strong coupling scale of the theory. And if you want the scalar field to be the dark energy, it needs to be some combination of M Planck and H naught. So it again needs to be a very light scale, 10 to the minus 3 eV. So, and this term, so this seemingly innocuous Lagrangian is actually very, very interesting when you start considering, for instance, neutron stars. So here, what I'm plotting is the gradient of the scalar field, which you can interpret as the 5th force due to the scalar field in the presence and in the absence of these nonlinear terms. So the dashed line is without the terms beta and gamma. This is what we call Brans-Dicke theory. It's been around for 70 years, or actually 100 years, dating back to Fierz and Jordan in the 20s. And the effect of the nonlinear terms is the red line. And as you can see, the 5th force, so in the x-axis is the radius, the distance from the center of the star. And as you can see, there is a suppression of this scalar force. There is a suppression until large distances from the center of the star, 10 to the 11 kilometers. And this is what we call the screening radius. So the effect of these nonlinear terms is to suppress scalar effects near matter sources. And these scalar effects are instead left free to do whatever they want and cause, hopefully, a dark energy-like phenomenology on large cosmological scales. So in the last 2 minutes. No, that's a good point. No, it doesn't. you need specific signs. And to be fully transparent, if you do positivity bounds on flat space and ask what are the signs that you need, they're not those. They are the opposite. So you need a non-standard UV completion that perhaps violates locality or Lorentz invariance if you want to UV complete this theory. That's a good point. And that's to me the most interesting open problem, how whether you can UV complete this. Certainly you need a non-standard UV completion, or there are, yeah, I don't know, maybe there are loopholes in the calculation when you include, because this calculation of positivity bounds are done in the absence of gravity. So you can actually, there is a paper by Claudia Duran where she shows that you can violate those positivity bounds by powers of 1 over the Planck mass. So, yeah, but that's a good point. So how much time do we have? 5 minutes? 5 minutes, okay. Yeah, okay, so I'll just show you the results here. So the presence of those nonlinear terms makes the task of doing numerical relativity evolutions much more complicated. So I put this slide for Rami because he was asking me about the Cauchy problem. So I blame him for the delay. Yeah, so here you don't even need to do, yeah, okay. So here we are treating it as an exact theory because that's what we do normally, and also because we don't know how to UV complete it. So what is the Cauchy problem looking like? So Cauchy problem means initial value problem. So we want to put this in a computer and do binary evolutions, compute gravitational wave emission. So what you need to do to study the well-posedness of the Cauchy problem is to put this into a first order form. So you write your PDEs. So here I'm only writing that for the scalar field, but we do it for gravity as well. So you write it in first order form, and then you compute the eigenvalues and eigenvectors of your principal matrix. And it turns out that in general, the Cauchy problem for this theory can break. So in particular, so you would like in order to have well-posedness, you need to have a complete set of eigenvectors and real eigenvalues. But it happens that along the evolution, these eigenvalues can become zero and the problem becomes degenerate. So these theories transition from hyperbolic to parabolic or even elliptic character. And sometimes also the characteristic speeds can diverge. So this is, the first problem is called the trichomy behavior. So it's because there is an equation in mathematics called the trichomy equation, which shows a similar transition from hyperbolic to parabolic or even elliptic character. And the second problem, the second breakdown is called Keldysh behavior after the Keldysh equation, again, an equation known in the mathematical literature. So to make a long story short, we can actually solve both these problems. So the first problem we solve by including this cubic term. So if you include this cubic term that I showed you in the kinetic term, we show that analytically that this transition to parabolic and elliptic character can never take place. Whereas this divergence of the characteristic speeds, which we fix by a choice of gauge, because here, these characteristic speeds depend on the shift, so we find a shift condition that fixes those. So I'll skip all these slides, which I think are interesting, UV completions, and just show you the results. So this is perhaps, I have 2 more slides and then I'm done. So to make a very long story short, so we come up with a formulation. We use, in fact, a standard formulation for the Einstein equations. We use the 1+ log slicing condition for the lapse, the gamma driver shift condition for the shift, and we find that this avoids divergences in the characteristic speeds. And using those, we can actually produce mergers of binary neutron stars in these theories. So there are not many theories for which we can compute the nonlinear evolution of binary compact objects. This is, as far as I'm aware, essentially the second simulation for binary neutron stars beyond GR. The first one being in. Yeah, these are perfect. No, sorry. Here there are also baryons. There are also, but you can't have solitons. Yes, sorry. I mean, it's not. It was not clear. So we're not talking here about solitonic boson stars. So here we have neutron stars with a scalar configuration on top. It's yeah. So okay, last slide, I promise. So Tanya talked about dipole emission. So in general, when you have scalar tensor theories, you have dipole emission of scalar gravitational waves. And what we find, and in fact, this is what happens, for instance, in Brans-Dicke theory, which is again the plain vanilla deviation from GR that has been around for a century now. When we include these nonlinear terms, and when we send the strong coupling scale to the theory to small scales, which is required by cosmology, dipole emission is suppressed. So screening, which acts at screening scalar forces in the static case, also works in the dynamical case and suppresses dipolar emission. However, we also find that screening is not efficient at preventing the emission of quadrupolar scalar waves. So this is what is shown in this figure. So the Brandstike, the unscreened case, Brandstike is red. And when we turn on these nonlinear terms, we actually have an enhancement of this quadrupolar gravitational wave emission. So we also have an analytic proof of this, which is not published yet. Yeah, I think I'll stop here. So this is in principle behavior that we could detect with third generation detectors such as ET, and perhaps possibly in binary pulsars. So I refrain from saying that these binary pulsars exclude this behavior because of course our simulations are for the merger phase, whereas binary pulsars are at very large separations. I'll skip also this lesson for self-integrating Broca fields. I'll skip all the part on scalarization. Yeah, so I was only able to give a fraction of the talk I wanted to give. I blame Paolo for this because he wanted me to put all this in the same talk. But I hope I have convinced you that scalar fields produce a rich phenomenology when it comes to compact objects, both in isolation, in binaries, in the presence of baryon configurations as solitonic fields. So I talked about superradiance, and this gives strong bounds on, I think, on light boson masses, boson stars. Screening, I didn't have a chance to talk very much, but this is very important if your theory, if you want your theory to be an effective field theory for dark energy or dark matter, for that matter. If you want a scalar field which is active on cosmological scales, you want to screen unwanted deviations from GR on local scales. I didn't get a chance to talk about scalarization, but Tanya already talked about it. So scalarization is probably testable by third generation detectors or by 3G plus LISA. So I think the prospects for testing all these theoretical ideas are good. Question is whether all this is, if you want, theoretically sound, and this is something that I'm happy to discuss with people who are more knowledgeable than me on the topic, and I'm happy to take any questions or comments that you may have.
So even if there were a lot of boson stars in the universe, we will also have black holes because of the mergers. There is no way you can prevent black hole formation in this theory. I mean, it's classical theory.
Yeah, you can also have black holes with scalar wigs. There is a whole lot of work by Carlos Herdeiro on how you can construct, if you have a complex scalar field with a potential, you can construct a black hole and then a wig, a scalar configuration around it. There's also the question of how boson stars, how do they accrete? So black holes are known, we know that black holes exist because we see quasars shining. So how do boson stars, what happens to a boson star when it accretes? Probably a black hole will form in the center. Yeah.
The way you could see the visible, the light, the visible or electromagnetic.
No, what I was saying simply is that, I mean, astrophysicists thought knew black holes existed since the 60s because there is no other way you can explain why quasars are so luminous. They have an efficiency of from 1 to 10%, which is much higher than nuclear reactions. So you can't explain the luminosity of quasars with the nuclear processes like in stars. So people thought these are black holes that accrete. So now the commonly accepted explanation is that there is a lot of gas accreting onto black holes. Now, if you have a boson star, if you replace the black hole with the boson star, the gas will still fall in the boson star, but it cannot be eaten by the horizon because there is no such horizon. It will probably accumulate in the center, and then because of the Hooke conjecture, it will form a black hole. So you'll end up with a black hole in the center and a boson star around it, probably. If it's this, well, but yeah, the scalar field should be minimally coupled to matter. So I doubt the infalling matter will do anything to the scalar field. But this is something that I think people in this crowd should keep in mind. If you want to replace black holes, you shouldn't be forgetting that black holes, we know black holes are there because we see them as quasars. So what happens to fastballs or to whatever the other exotic black hole mimicker when they accrete?
So you have a good amount of degrees of freedom in the system. All these problems to reveal, okay, there are some examples, but remember the break configuration from the mass to the motor space, they depend on arbitrary functions of several variables. So when you can put energy into them and energy just goes into these degrees of freedom, then it's not easy. So what the question that people ask, what the question is asking, in the sense that we know very well how to answer that for the microsystem solution. My main question is, I'm asking because I'm trying to understand how much doing microcontrollers is very painful. So yes, no communicate doesn't solve terrible things, and it's a very painful thing. I'm just trying to understand how much mileage can I get by using boson stars instead, what phenomena can I capture by using boson stars instead, not going to the whole machinery computer.
I see, okay.
That's why we know all the phenomena discussed, how to answer very well. I don't have, personally, I don't have any question about that. Maybe other people have, discuss. But as far as I'm concerned, I think the solution is here built with the people, the risk, and the ones that have. Any example, I think the answer about the questions. I don't think there's any mystery about that. The only question is, for example, if boson stars, how much mileage can I get? Not solving, half a page.
No. Definitely, it looks like boson stars do not behave the same when it comes to accretion because you don't expect.
But for example, there's some
But
no, I just have one question.
stars, yes.
So if you fastball, if it accretes, then it should come out, right? Because whatever goes in.
Sorry, I'm changing something. There are some systems that have rays, and the rays come together, right? And they look something with the deep breath. So when they go on the deep breath, there's a huge amount of degrees of freedom which are localized at that position. So if you throw something in, it goes into these degrees of freedom which are localized inside the microstate geometry or inside the fastball, and it doesn't come out. And to come out, you basically have to convince a huge amount of this.
No, but
freedom is combined to get something to go.
But
the bigger the black hole is, the harder.
But if nothing comes out, how can you falsify that theory? How can you distinguish it from a black hole? I mean, for all practical purposes, it will behave as a black hole, right?
But you're saying the time to get out very long.
Yes.
But how long? I mean, because these quasars are there for, millions or billions of years. So what I would expect that if they are fastballs and not black holes, the rate at which, the quasar, the luminosity should be more if it is a fastball than if it is a black hole, right?
No, it's not there.
I think we agree, that songs look like a black hole. Any proposal should look like a black hole. They all fastball solutions have parameters, and you can this parameter in such a way that it can to escape from the level is very similar. Everything is agreed with the experiment field.
No, I completely agree. I'm just asking that if it is a black hole, so how can we test it? So in all purposes, if fuzzball is same as a black hole,
No,
how?
I wouldn't say the same. I'm not
I mean,
saying that they-
I agree. I mean, theoretically, they are very different, but observationally, how can we test it?
So for example, the one from one is different. Because you're basically screening this very complicated large number of degrees of freedom and you know, the multiple numbers, there's something very much.
Sure, sure. And that is the only thing, I mean, that,
One of the things, and you know, prior version of that, like an version of.
Like this, I think, the like this of the path is different from the one of the platforms. In principle, I don't know how many.
Don't know, you know, there.
okay.
Multiple numbers together,
But again, you don't
Thank you.
understand I mean.
Sure, sure.
So I would like to add to the discussion on the boson stars because I think it's interesting. I think the argument is old about the quasars and so on, but I'm not sure it's really supported by simulations. It's easy to just
Well,
and
what
it's
simulations.
well, it has been done to do
But that-
MHD with boson stars.
No, yeah, there is a paper by Rethel where he claims that this is emitted
Yeah.
as jets.
Yeah,
But
so
he doesn't follow this
that's
in
right.
long
but I'm-
term when
yeah,
the
but
jet
I'm saying
comes
if you
back.
want to I don't think it's straightforward to rule out alternatives like boson stars when explaining supermassive objects. I think a lot of work and modeling needs to be done.
No, exactly. If you want to do it well, yes, but are you willing to put the time and resources
That's a
to
different
rule it
question.
out?
Yeah, yeah,
Because I
that's a
think that's a
different question.
sociological
Yeah, yeah,
question.
yeah, yeah. Sure,
The
sure,
reason
sure,
It
sure.
hasn't been done.
I
in
agree with that.
sociology.
But that's, yeah, but I'm just saying it's also maybe a bit too rushed
No, yeah.
to just rule out this.
No, even as